Should be able to go through this pretty quickly. This stuff, now it's just step 2, I guess, right? Like our next iteration of rotary motion. So everyone knows circumference of a circle is 2 pi r. 1 revolution is 2 pi radians. We know that from yesterday or 2 days ago. No, yesterday with you guys. When a wheel does 1 revolution, the distance it covers is the circumference, which is 2 times pi times radius. And we know that, right? Okay, so let's go ahead and go right into the business here. What is the linear velocity of a wheel spinning 5 revolutions per minute with a radius of 20 inches? Okay, so how do we do those problems like this? 5 revolutions per minute. I do my little deal there. And then I go, in 1 revolution, I cover how much distance? 2 times pi times 20 inches, because that's the whole circumference. If I wanted it in radians, I would just go 2 pi radians, and that would be radians per minute. But there it is, and they didn't tell me how I want it. I'm going to leave this answer in terms of pi. 2 times 20 is 40. 40 times 5 is 200, because 5 times 4 is 20. So 200, put the pi next to it, inches per minute. If you want to write it in terms of not pi, then 200 times 3.14, whatever that is. But that is the exact answer. How do we feel? Okay, and then it says, what does it say next? What is the angular velocity? How many different ways can we express the angular velocity? All right, they didn't tell me what units to use, so I'm going to write angular velocity. The first one that is obvious, I hope, is 5 revolutions per minute. That's not the only way you can express it. If you wanted this in revolutions per hour, 5 times 60, what's that, 300? You can say 300 revolutions per hour. If you wanted this in radians, then I would go 5 revolutions, and then 1 revolution, there is 2 pi radians, and this is still in minutes. So 5 times 2 pi, that's 10 pi. So you would go 10 pi radians per minute. Dot, 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 keep going. There's others. You can do it radians per hour, et cetera, et cetera. I think we're pretty good at that. I don't think we need to talk about that much more, right? Are we okay? What's up? Well, what's it again? Like 1 revolution is 2 pi radian? Oh, I just did 5 times 2 pi, and I got 10 pi. You know what I mean? Any other questions, guys? What's up? I did 5 times 2 pi because that's angular velocity. And anything that deals with rotation is angular, and radians deals with rotation. If I would have told you I do 360 degrees every half a second, so then that's angular velocity as well. You know what I mean? Did I answer your question? I don't even know if I answered. I just, yes, 5 revolutions per minute was given, times 60, I got 300 revolutions per hour, divided, or times 2 pi, I got 10 pi radians per minute. All 3 are examples of angular velocity. All right, I'll do my best to draw. I'm not the best drawer. 2 rotating objects connected by an axle. So here is a wheel in 3D. I'm not very good at 3D there. Does that look like a wheel? It's connected to an axle. My axle is not super cool. Let me draw a better axle. An axle is like a cylinder. I guess you can, right circular cylinder. And here's another wheel, but this one's smaller. It doesn't look 3D to you guys? I did fail art, so in case you're wondering, yeah, I did. I failed art. It's actually in my transcript. You didn't fail art. Pretend this expo marker here is axle. So imagine a big circle. I don't know. Imagine like I cut this paper out in a big circle, and I put a little circle on this side. If this axle rotates 1 revolution like that, then the big circle does 1 revolution, and the little circle does 1 revolution. Do you guys agree? Perfect. So there it is. So it says 2 rotating objects connected by an axle have the same angular velocity. An easy way, what's connected to a bike wheel? The chain in the back sprocket like we did last time, right? Okay. Two rotating objects connected at the rims have the same linear velocity. Okay, that looks like this. Big circle, little circle. And they're connected by teeth on the rim, right? Usually, like teeth drive the other one. And these have the same linear velocity on the rim. Does that make sense? What else has the same linear velocity? Well, let's see. Little circle, big circle, connected by either a belt or a chain. Belt, chain. This also has same linear velocity at rims. When I say rims, at the exterior of that circle. Does that make sense to everyone? Okay. If you understand all three of those situations, then I think you will be good to go. Don't freak out. Today, don't worry, today's a short day, so I gave you guys pulleys, but a simple pulleys. On Monday when we come back, or Tuesday with you guys, we'll have a question that has several pulleys, and don't freak out, you just do one at a time. Cool? All right, so here we go. Go to the next page. I got two pulleys with one belt. So we're just gonna do one at a time, guys. The small pulley has a diameter of 10, so that means my radius is 5. So that's what I think is more important, the radius. So that distance there is 5 centimeters. And I'm rotating at 100 revolutions per minute. So I'm going to write that somewhere close to this. 100 rev per minute. That's how fast the little guy's going. Are we okay? All right. Let's see what this says. Find its angular velocity in radians per second. Okay, here we go. 100 rev per minute. And in one revolution, I do how many radians? Perfect. 2 pi radians. I have radians per minute. I'm almost done, not quite. I want radians per second. So I want to cancel out the minute, so I put a minute in the top. In 1 minute, there is 60 seconds. Once you guys feel that you're good, you no longer have to do this T-chart. You can just work with dimensional analysis directly. If you want to go ahead and do all questions like this, that's fine for now. Well, it's fine forever, but I would like for you to drop it eventually. Okay, take your calculator, go 100 times 2 pi, whatever that is, divided by 60. Here's my calculator. 100 times 2 pi. Yeah, you can leave it in decimal or in pi, they're both the same. The pi is actually leave it in terms of pi is actually better because it's exact. 10.47197. 10.47197 radians per second. If you leave it in terms of pi, that's actually probably better but that's fine, no big deal. How do we feel? What's up? Why didn't I do what? Oh, whatever I have in the top, I multiply, right? So 100 times 2 pi. And then whatever I have in the bottom is what I'm dividing by. So I just did 100 times 2 pi and then divide by 60. Did I answer your question? Because I don't know. Well, I don't know what the question was. Can you say it again? Yeah. And then 5? Oh, because if I put 2 pi then 5, then that would be a linear distance. Because 2 pi times 5 is how much distance you cover when you do one revolution. I don't want linear. I want angular. I want radians. You know what I mean? Yeah, I know. All right, letter B. Okay, so here it is. For letter B, you would do that. Find the linear velocity of a point on the rim of the 10 centimeter pulley. So here's the hack. The hack that I told you guys is to just take the answer that you just got, and in 1 radian, you have how many centimeters? 5. So I would just go 10.47197 radians per second, and in 1 radian, you have 5 centimeters. So I take my calculator, and I'm just going to go that times 5. 52.35987. So let me write that down. 52.35987 centimeters per second. Now, if that does not make sense to you, if you're like, I don't know why 1 radian is 5. Well, literally, radian means radius. But if you don't like that, check it out, Ms. Guajardo. You can always do this. You can go, how fast was that rotating? 100 revs? 100 revs per minute. And you can go in 1 revolution. I cover 2 times pi times 5 centimeters. See, so now you have centimeters per minute. And if you want to have it looking like this one per second, in 1 minute, there is 60 seconds. And if you think about it, look at the calculations. It's really the same thing. 100 times 2 pi, that would have given you the number that you got up there, times 5, well, divided by 60 would have given you that. And then whatever you do, divide by 60. It's the same calculations. Do you guys see that? Cool or not cool? Okay, perfect. All right, let's go to the next one, guys. Find the linear velocity of a point on the belt connecting the 2 pulleys. Yeah, it's going to be the same, guys. A point on the belt. So what did we do earlier? We found the velocity on the rim. And now, isn't that rim touching the belt? Yes. So then that belt must be going the same. So we're going to say same, comma, 52.35987 centimeters per second. How do we feel? Find the linear velocity of a point on the rim of the large pulley, which has a diameter of 30 centimeters. So let's go to the large pulley. The diameter is 30, so that means this radius is 15. That belt is connected to the large circle, so my linear velocity must be the same. Same. 52.35987 centimeters per second.
Let's say like you didn't know that and you put it into the same way, like the first one. Would you put it in the answer?
Yeah, what?
Like let's say I didn't know that they were both the same for some reason with that test. So I just did it the same way I did probably. Would I put it into the answer or
No,
no?
because you got the revolutions for the first pulley, not the second. Are we still okay? All right, letter E. Find the angular velocity of a point on the rim of the 30 centimeter pulley. Okay, so let's look at our picture first. Does everyone agree that every time the little one does, or every time the big one does 1 revolution, the little one is doing more revolutions? Yes. All right. So we know that. How would I have done it? I think if I were taking a test and I were going fast, I think I would probably go like this. There's other ways. I'll tell you the other way in a little bit. 52.3598 centimeters per second, because that's the linear velocity of that big one, right? And then I would say, how many centimeters are in a radian for that one? For that pulley. What's the radius? So I will write 15 centimeters in 1 radian. And there it is. I have it in radians per second. So I'm going to go to my calculator, and I take that number. I already have it there in my calculator. And I divide it by what? 15, and there it is. 3.49065. 3.49065 radians per second. I want that angular velocity for the big pulley. All right. That's anything, yeah. All right. Chavez, is there another way to do it? Yes. So don't write this down, just listen, and after you take this in, then you can write whatever notes you want on this subject matter. You guys ready? If you know the scale factor between this one and this one, you can find the angular velocity for the big wheel. Well, how do I know it? Let's see. 15 divided by 5. What's that? So that's my scale factor. So what does that mean? Every time the big wheel does 1 revolution, the little one does 3. So what can I do? I can take this 100 revolutions per minute. Now be careful, don't go fast, because this is where mistakes are made. Do I multiply by 3 or divide by 3? Divide, because it's going slower, spinning wise. So 100 divided by 3, do you guys agree that's 33 and 1/3 revolutions per minute? So that would be a valid answer here. So don't write this down, guys, just still listen. This is a valid answer, 33 and 1/3 revolutions per minute. And you might say, Chavez, that is not the same as this. And then I would be like, yeah, it is. It's the same. If you turn this revolutions per minute into radians per second, do you think we're going to get the same answer? We are. So check it out. I'm going to go alpha y equals number 2. And I'm going to go 33 and 1/3. And check this out, guys. That's how many revolutions per minute we're doing. In one revolution, how many radians are there? 2 pi. So there's, 2 pi. This is my radians. And now I'm going to divide this. This is how many total radians. I'm going to divide this by what? 60 to get seconds. And let's see if we get the same thing. If we don't, I'm a fraud. And look at that. Dude, we get the same exact digit per digit. Yes. So it doesn't matter how you do it. You'll get the right answer. As a matter of fact.
I want to see you demonstrate 33 and 1/3 revolutions per second.
Well, I mean, I can't rotate 33 and 1/3. Not in a second, at least. But there it is. Does that make sense to you guys? So, by the way, I would accept this answer. This answer here, if you leave it alone, that's correct. I'll take it because it's angular velocity. Does it tell me what units to use? No. As long as you understand, you give me the right units, that is angular velocity. Cool or not cool? Cool. I think we're winning, guys. You can write whatever you want to write down from that thought process.
I think that's super cool.
Oh, they like your shrine. We're gonna leave it there until someone. No one's gonna take it down. It's gonna stay there probably forever.
I was a baby, child.
No.
I was a baby. I was in my 20s.
All right, we're gonna finish this real quick. Letter F. Find the angular and don't worry, we're almost done. Find the angular and linear velocity of the point at the center. So the angular velocity, is it the same? Yes, angular velocity is the same everywhere for that one, guys. So I'm gonna say same, and I'm gonna say either 3.49065 radians per second, or you can say 33 and 1/3 revolutions per minute. It doesn't matter what answer, as long as you give me correct units for angular. Now, what about the linear? At the center.
Oh, sir, I didn't hear that.
At the center, it's what? And make sure to put units. Don't just put 0. Yeah. I mean, if you want, you can say miles per hour if you wanted to, because technically you're correct. But make sure to put units and make sure those units are distance divided by time. How do we feel? Okay, we have a little activity. We're a little short on time, so it depends on how fast you are. But I think you should be able to finish it overall. If you have any more downtime throughout the day, you can use it to finish it up.